In this video, I want to do an example of applying Newton's laws on a single object. So, in this case, I have some large block that's not attached, but just resting against one side is a smaller block. And I want to know how this large block is going to keep the smaller block from falling. So the smaller block has some mass m. And so I might ask, is there any speed at which I can move this object to keep this small mass falling? So if this large mass moves very quickly, how fast does it have to go at constant speed to keep the mass from falling? So to do this, we're going to do a force analysis on our objects. The first is to choose an object, so I'm going to choose the small mass here. That's what I want to keep from falling. And so I want to analyze the forces then on that object. So there's going to be the force due to gravity. Then the only other object touching it is the large mass. So there's a contact force between the large mass and the small one, and the block. And so I'm going to break that contact force. This is gravity. Because I think it's the friction that's going to keep the mass from falling. So I'm going to break up this contact force into the normal force and then the friction. And I'll call that F sub small f. And nothing else is in contact with the small mass. I'm ignoring air resistance. That's kind of key, isn't it? Ignoring air resistance or drag. And I want to do a force analysis on this system. Okay, there are my three forces. So my next is to put them on a free body diagram. So I want the force due to gravity, which is towards the center of the Earth. The normal force is perpendicular to the surfaces. It points from the agent to the object, which is this case. The agent is the large mass. Object is a small block. That's the normal force. And next is the frictional force. So the friction acts in a so it's static friction. Since I want to keep the system from moving, I want the condition where the two masses are at rest relative to each other. So in our contact force model, the force due to friction points in the direction opposing the motion that the object would move relative to the agent if there were no friction. Okay, that seems kind of cumbersome, but let's walk through it. If there were no friction, then we would believe this mass would fall. And so the frictional force would be in the and that's the direction of the motion of the agent, the direction of the motion of the object, which is the small block, relative to the agent, which is a large mass. So it would the object would move down. So the frictional force is going to be in the opposite direction. So that means that the frictional force is up. So there are my three forces on my free body diagram. I need a coordinate system. I'll put my coordinate system up here, just so it's out of the way. And so I'm going to have the positive x going to the right and the positive y to be up. With my coordinate system, I can now do a look at the vector sum of all my forces. And as you get practiced, and as these, especially for simple diagrams, such as something like this, where all the forces are along the respective axes, you can skip some of the steps go much faster. But I'm going to continue with adding all my forces the way I've been doing. So I'm one at a time. So I have gravity, and it has a 0 magnitude in the x direction. It has a magnitude of mg in the y direction. That's an entire magnitude. And given my coordinate system, that's negative. My magnitude's positive, but my component is negative. Okay, so next is going to be the normal force. It has its entire magnitude, which is positive, along the x, and that's 0 in the y. My force due to friction then has 0 in the y-axis, in the x-axis. But now it has a magnitude equal to the coefficient of static friction times the normal force in the y-axis, and given my coordinate system, that's positive. Now the sum, the vector sum of all of these forces is the mass times the acceleration. Now I want the condition where the block is not falling, and so the y component of the acceleration is 0. And so then there may be some acceleration in the x direction. So this vector sum, the sum of my forces equal to my mass times acceleration, now gives me some relationships between my parameters. So I have that the normal force is equal to mass times the acceleration, and then I have that the static friction times the normal minus mg is equal to 0. So the first thing I recognize is I can answer my first question, which is there any constant speed, ignoring drag, where the mass does not fall? And the answer is no. At any constant speed, if v is constant, then a is 0. If a is 0, then n is 0 from here. And if n is 0, then the frictional force is 0 here, and you simply have the force due to gravity and it falls. Now, we know that the drag force would in fact contribute then to help keep it on there. If it were, it could contribute a normal force. But ignoring the drag, then there is no velocity at constant velocity at which the mass stays. But there is, of course, though, an acceleration where that happens. So how must the large mass accelerate the block such that it stays? Well, it has to maintain a normal force to maintain that acceleration, and so we can solve for n and put that in this expression to eliminate n, and then we can solve for the acceleration necessary so that the block wouldn't fall. I'm assuming here, again, that for my conditions, I know the mass of my object. I know my coefficient of there's a coefficient of static friction between the blocks. What's unknown really here is the normal force. And so this becomes mu sub s times ma minus mg is equal to 0. The m's cancel, and I get a is equal to g over the coefficient of static friction. So that's the acceleration that must be applied to the block to keep it from falling. Okay, so that was kind of a straightforward example, but one where we went through all the steps. I'd like to expand on that a little bit and do a variant of that problem. So in this case, I want to, again, keep the mass from falling, but instead of moving the mass, that's too small a picture. Instead of the mass moving horizontally, the mass is moving at some angle, theta, below the horizontal. How does this affect the acceleration that must be exerted, well, the force that must be exerted on the small mass to maintain an acceleration such that the mass does not fall. It stays at fixed relative to the large mass pushing it. Okay, well, we can go about the same thing. And so I'd like to point out sort of how this is fitting into the general problem-solving strategy, how sort of our approach to solving the Newton's second law problems. You always have to have a picture. You always have to have a really good visualization of what's going on. And then solving for the forces and the free body diagram is, again, part of that visualization and brainstorming process. We're establishing relationships between the parameters. Only after we establish sort of F equals ma do we then have a sort of an approach to solve once we've established all those relationships. And then it's the important matter of sort of checking our result to see if it makes sense. Okay, so here the forces on the object are the same. We have the force due to gravity, and then a contact force between the two blocks. So I'm not going to rewrite them, but there's a normal force and a frictional force again. And so now, if I can draw my free body diagram. Okay, at this point I want to introduce something very important. I have now the motion of an object that's not perpendicular or parallel to the Earth. Gravity plays a role here, but the motion is in some other dimension besides parallel or perpendicular. So when I do that, when I encounter that, when I always on my free body diagram get both axes. So let me get an axis that's and big pictures, lots of space. So here's my axis, parallel and perpendicular to the ground. And then I want a new set of axes that's parallel and perpendicular to the motion. So if it's coming down in some angle, there's the axis parallel to the motion. Here's the axis perpendicular for the motion. And I get all four, essentially 8, each set of axes on my free body diagram. All right. And so now, and then I can identify this angle is what I'm given. This is the angle that I know. And I need to be able to accurately translate that angle to my free body diagram. This is terribly important. And there's no other way to do that except to accurately visualize what you're doing, to have really good pictures, and to be able to then translate this from a graphical to your or pictorial to sort of your schematic representation, which is the free body diagram. So if this angle is theta, that corresponds to this angle here, theta. Once I've identified one of those angles, I can identify all of them. When I make my diagram like this, once one angle's theta, then all the other are theta. And then the alternate angles here, sort of this angle, get it out of the way here, this angle is 90 minus theta. And so I now know all the important angles, and I've identified where they are in my figure. Now I go ahead and put in my forces on my diagram. All right, so now I have the force due to gravity still points towards the center of the Earth. That's here. My normal force now is perpendicular to the surfaces, pointing from the agent to the object. So that's in this direction. So that's my normal. And now my frictional force is tangential to that surface, and it's in the opposite direction that it would go if there were no friction, and that's going to be sort of directed up the axis. That's the tangential axis that is more up than the other, and so that's the direction of the force due to friction. Okay, and now comes the critical time, which is you have to put your coordinate system on this free body diagram, and where should that coordinate system be? And now I want to give you a huge hint that you'll never want to forget. If you have motion entirely along one axis, like we have here, this is a two-dimensional problem, but all of the motion is along this line. You almost always want one of your axes along that line. You want your x and y axis to be parallel and perpendicular to the motion if you have motion that's all along one dimension. Now there might be an exception, but they are very, very rare. This will almost always simplify your problem enormously. Okay, so now we have a coordinate system, and now we can do a vector sum of our forces. All right, so we have the force due to gravity. We'll do our force due to gravity first. Now, unlike before, our force due to gravity is not along an axis, so we have to find the components, which is fine. To find the components, I need the projection. I could go either direction. Draw a line from the tip of the vector to an axis where it makes a right angle. And now I need to find the components. I'll give you a different color. So my x component is going to be along the length of that red line. It's also the length of that red line. And so since I know that this angle here is theta, I know that the x component is going to be the magnitude of the gravitational force, which is mg times sine of theta. And it's I hat, and if this is the origin, it's in the positive x direction. Now I need and I can also see that from my picture, if with this angle being theta, this angle is theta, and so I can calculate again, the length of this side of the triangle is mg sine theta, because the length of my force vector is mg. All right. And so I do the same thing for the y component, only now I'm interested in this length, and that length is, well, let's not get ahead of ourselves. That length is the hypotenuse, which is the magnitude of the force, mg cos theta, and it's along the y component. And from my picture, I see that this component is in the negative y direction. Again, I always go back to my picture, my coordinate system, to determine signs. Lengths, magnitudes of components, and magnitudes of vectors, I always get just from the length of the triangle, but components, I go to the diagram. All right. And so then my normal force is conveniently just along the x-axis, has nothing along the y, and my force due to friction then has nothing along the x. It has a magnitude due to my friction model of mu n, static, j, and from my picture, it points along the positive y-axis. So this all is equal to mass times the acceleration. The sum of all my forces is equal to the mass times the acceleration, which is then some m a I hat. And since it's not moving relative to the block, it has 0 in the j hat. Now you can see how important it was to have our coordinate system set up this way. If we had our coordinate system set up parallel and perpendicular to the axes, then we'd have acceleration components along both axes. And that makes things enormously more complicated. And so this way we've eliminated one of our components of the acceleration, and that helps. All right, so now we have two relationships among all of our parameters from our vector equation. And so that gives us negative mg cos theta plus mu sub s n is equal to 0. And we have n plus mg sine theta is equal to the mass times the acceleration. All right, again, I want to solve this for n, and then substitute it into here to see what sort of conditions on the acceleration do we need. All right, so I've solved for n. I have mu sub s n is equal to positive mg cos theta. I bring this term on the other side, and so n is equal to mg over mu sub s cos theta. All right, so I can substitute that in. I have here mg mu sub s cos theta plus mg sine theta is equal to ma. My m's drop out, and I have a solution for a. But that's not. I want to look at this. I want to understand what that means. The first thing that I want to look at is I want to compare it to what I did before. So before, when it was going horizontal to the ground, a was g over mu sub s. In fact, that's right here, g over mu sub s. So let me rewrite this a little bit. If I multiply this term by mu sub s over mu sub s, then I can factor out from this expression a factor of g over mu sub s. If I do that, I get, so over here, a is equal to a factor out g over mu sub s times cosine theta plus mu sub s sine theta. Now I understand that this is not the sort of thing that a new student is immediately going to think of. But this is the sort of thing that good problem solvers do. And so you want to take note of it and start developing these skills. Now I have an expression that I can really look at to see what sort of physical meaning it's telling me. So this is the same term that I had before when it was horizontal, only I now have another term that's a function of the angle that contributes to what the value of the acceleration is. And so now, to check to see whether it's right, I invoke something else that very good problem solvers always take advantage of. Limiting cases. So I have this result, and the first thing that I ask when I see something like this is that, does this give a result that makes sense as theta goes to 0 or theta goes to 90 degrees? Why does that matter? Because I've never forgotten my original system. A very good visualization. I understood what was going on with this picture. And sort of the limiting cases are when theta equals 0, when it's perfectly horizontal, and theta is equal to 90 when it's going straight down. So what does this result give me in those limiting cases? And so this is where I'm checking the part. So the first is going to be theta is equal to 0. At theta is equal to 0, sine theta is equal to 0, and cosine theta is equal to 1. And so I get a is equal to g over mu sub s, which agrees exactly with the result I had before. So that's excellent. And so at theta is equal to 90 degrees, in this case, cosine theta is equal to 0, sine theta is equal to 1, and my acceleration is g over mu sub s times mu sub s. A is equal to g. And so that's telling me that I've got to, if I'm going straight down, to keep these two blocks in contact, I have to have an acceleration that matches the gravitational acceleration, which makes perfect sense. It means both blocks are accelerating at the same rate. So now I have complete confidence now that this answer is right. I've recast it in a form where I can understand what the what the terms of the answer mean, and I've explored limiting cases that both agree with what I know to be true, and so now I have confidence in my answer.